Repeated queries should not hit your full retrieval stack every time. Redis caching can cut latency, but only if the cache keys respect filters and freshness. This is the pattern you'll be able to implement by the end, which caches a search by query and filters, and then serves the cached results on repeat requests. I'm Professor Pi, teaching search and IR with simple Python. Think of a search API that answers user queries over thousands of documents. Every repeat query that runs the full ranking pipeline costs CPU and adds milliseconds. At scale, those milliseconds add up to unhappy users and higher bills. A cache sits in front of the heavy work and returns results instantly when nothing changed. The trick is to cache safely. If your cache ignores filters or index changes, you will serve wrong results. Success looks like faster median latency and no incorrect hits for filtered requests. At a high level, the idea is simple. We will build a tiny search routine that ranks by token overlap. Then we will layer a Redis cache. First, we show no cache, then add a basic cache, then make keys filter aware, then add a versioning switch to expire large groups, and finally split retrieval and rerank. This keeps cached results correct and fast. Now we run a tiny baseline search to show the problem. This snippet connects to Redis and runs a tiny baseline search without caching. The code creates a redis.Redis client and verifies connectivity using r.ping, which returns true on success. A small docs list stands in for an index with IDs, text, and a tag used for filtering. The search function tokenizes the query, filters candidates by the optional tag, computes a simple token overlap score, and sorts results by score and ID. We execute one search for the tag DB and take the top result. Increasing K would return more results, which can raise downstream latency without caching. The printed values confirm Redis connectivity and show the current best match before we add a cache. Next, we add a simple cache that keys only on the query and K. This example adds a Redis-backed cache for repeated query results using r.get and r.setx. The QKey function builds a compact key from the query and K, so identical requests map to the same entry. The cached search function looks up the key with r.get. On a hit, it returns the cached IDs immediately. On a miss, it executes the in-memory search, then persists the comma-separated IDs using r.setx with a time-to-live TTL to bound staleness. We first warm the cache, then call the same query again to demonstrate a hit. Longer TTL increases reuse but risks stale results. Shorter TTL refreshes more often. The print shows a hit and the returned IDs. Now we make sure filters never collide in the cache. This code makes cache keys filter aware, so different filters never collide in Redis. The fkey helper encodes the tag into the key, and cached search F forms a full key that includes query, K, and the filter scope. It checks Redis with r.get. On a cache hit, it returns the stored IDs. Otherwise, it runs the search with the given tag and writes results using r.setx, isolating entries per filter. We first warm a DB-scoped entry, then request the same query with the ML tag, which must miss and populate a new key. This prevents leaking wrong filtered results across users. The printed miss confirms safe separation by filter. Next, we add a simple version number to invalidate many entries at once. This snippet introduces versioning with Redis to avoid stale results after data or ranking changes. The ver function reads a global version from the key search ver using r.get defaulting to 1. The cached search v function appends that version to each cache key, ensuring entries are namespaced by the current index or filter logic. We warm a db scoped entry at the current version, then bump search ver atomically using r.incre, which increments the integer stored at that key. The next identical request must miss and refresh under the new version. Increasing the version invalidates all prior entries at once. The printed miss under version 2 shows safe, immediate invalidation. Finally, we split retrieval caching from a lightweight rerank. This example splits caching into a reusable retrieval tier and a lightweight rerank step. The function toTier builds a retrieval key ret that includes query, filter, and current version from ver, then checks Redis with r.get. On a miss, it runs search and stores the candidate IDs using r.setx for a longer TTL. The rerank step applies a simple rule that prioritizes texts containing the boost token, simulating personalization or recency signals without changing the retrieval cache. We warm the retrieval cache and then hit it, computing saved milliseconds only for the skipped retrieval. The printed hit and saved MS show compute avoided while preserving correct top results. This toy flow maps directly to a real system where retrieval is expensive and rerank is cheap. Use the retrieval cache for shared state across users, and apply rerank locally for per-user signals. The same keys and versioning idea scale to larger indexes or ANN stores. Recap in 3 quick points. What it is: a Redis cache that stores search candidate IDs by query, filter, and version, so repeats skip heavy work. When to use it: when your retrieval or ranking pipeline is costly and many queries repeat with the same filters. One caveat: caches can serve stale data if you do not increment the version or set appropriate TTLs. Next step: measure latency while increasing the retrieval TTL, and then tune the rerank rule or the version update cadence to balance freshness and hit rate. If short, practical IR helps, subscribe and watch the IR videos.